Well, it's a great privilege to be here, to be asked to give this lecture, and thank you for that very positive discussion. So what I want to do is I want to talk about the nature of cosmology today, and I'm going to have 5 parts to this talk. Firstly, cosmology is today a precision science with masses of high-quality data, ever increasing our understanding of the physical universe, and I will summarize that because I'm assuming that some of you are not cosmologists. Secondly, paradoxically, theoretical cosmology is increasingly proposing theories based on ever more hypothetical physics, or that are even untestable in principle sometimes, and so I will discuss that a little bit. Thirdly, we are also seeing ever more dogmatic claims about how scientific cosmology can solve philosophical problems that have been with us for millennia, and so I will say something about that. Fourthly, this leads to what is and what is not testable in scientific cosmology, which is something I've been thinking about for many decades. And finally, what can we make of recent claims made about how scientific cosmology relates to issues of meaning? So to start with the first part, the universe is of vast scale, it's expanding, it started off in a hot Big Bang. Structures such as galaxy clusters formed by gravitational attraction, and stars and planets formed in this environment. Now that is a summary of a huge amount of work that has been done by a huge number of very, very talented people. None of these are obvious. So here's a star cluster in our own galaxies, a couple of 100 million stars. Here is a section of the Milky Way, our own galaxy seen edged on. Now, our own galaxy is like the Andromeda galaxy, which is this galaxy here, 100,000 million stars. You must ignore these stars. These are all in our own galaxy. So ignore this kind of veil of stars and look at the structure there, the Andromeda galaxy. It's about 50,000 light years across, which is about the same size as our own galaxy. It has 2 satellite galaxies. Now, to scale that, you must remember that the Earth to the Sun is 8 light minutes. The Proxima Centauri, the nearest star, is 4 light years, and so this is 50,000 light years. And the solar system is incredibly small and insignificant compared with our galaxy. This is Andromeda. If it was our galaxy, that is roughly where we would be. We're way out towards the outside edge. And that previous picture was looking from there, looking inwards towards the center of the galaxy. So this is our own habitat, our own galaxy. But there are millions and millions of galaxies we can see out there. They're very, very beautiful. These are interacting galaxies. Galaxies occur in clusters. There are a very large number of galaxies in clusters. This is the Hubble Deep Field. And this is a star, but everything else you can see there is a galaxy. Each of those tiny blue dots is a galaxy. And these great surveys we are now getting, these are surveys of particular parts of the skies. You can see thousands and thousands of galaxies with great walls and great voids. And we have in fact believed that we can see of the order of 100,000 million galaxies in the observable part of the universe, each with 100,000 million stars, and a huge number of those will have planets around them. So the Earth and this room are insignificantly small in this context. That's what is there. Now, what has been happening in terms of dynamics? The very famous paper by Hubble, 1929, he took the redshifts of galaxies. What you do is you take the spectrum of a galaxy, you spread it out through a prism, and you get it going from violet, indigo, blue, green, yellow, orange, red. You compare it with the laboratory, and you find these are these lines in the galaxy which are shifted. And the further away the galaxy is, the further they're shifted. That says it's moving away from us, the famous Doppler shift effect. Hubble was estimating the distance of the galaxy by its apparent size and the velocity from the redshift, which is shown these arrows. These arrows are bigger and bigger. As they get bigger, the galaxy size is getting smaller, and so Hubble plotted it to scientists too in a graph, and there is the velocity against the distance, and it's pretty much a straight line, and that is the very famous Hubble relation that velocity is proportional to distance. In other words, the universe is expanding, galaxies are getting further and further apart from each other. So now you take Einstein's field equations, which says that gravity tries to pull things together, kinetic energy tries to let them go apart, and which one wins. And in the universe, this is the scale of the universe against time, and there are three possibilities. If the gravity wins, there's not enough kinetic energy, the universe expands, gravity wins and pulls it back. So over time, that universe recollapses. And it turns out those have positively curved space sections. If there is not enough matter, if there's the kinetic energy wins, the universe expands forever. And it turns out those have negatively curved space sections. And in between, the ones which are on the verge of recollapsing, they are the delicate ones which just manage to expand, are these ones with flat three-space sections. Now, we measure that in terms of something called the density parameter. It's the density of matter divided by 3 times the rate of expansion squared. And that parameter is 1 for those values. It is less than 1 for those, and it is greater than 1 for those. So there's this density parameter normalized by the expansion. And one of the big things cosmologists want to know is, will the universe expand forever? Will it recollapse? What is going to happen to it? And in fact, we still don't know if the universe is negatively curved or positively curved or has flat spatial sections. That's one of the things we still don't know. Now, some new discoveries from the past couple of decades. This got the Nobel Prize last year. We could use supernovae in distant galaxies as standard candles. What happens is, at the end of their lives, stars, big stars, start to collapse. A huge explosion takes place, blows them apart. You can see that as a supernova, which becomes very bright in the sky, and those can be used to estimate distance. They are standard candles because their maximum brightness is correlated to their decay rate. Now, you measure their redshifts, as the same as Hubble did, and these give the first reliable detection of nonlinearity. In other words, Hubble put a straight line, and we wanted to know, did this curve bend up or did it bend down? And we all assumed, before this data came in, that the curve was going to bend down. In other words, that gravity would be winning and slowing down the expansion of the universe. But these redshifts gave the first reliable detection of this nonlinearity of the bending, and they showed it bends up, which shows the universe is currently accelerating. The expansion is getting faster and faster, and that was a totally unexpected result which caught the whole astronomical community by surprise. What it means is there's an effective positive cosmological constant that is a repulsive force which is making the universe accelerate, the expansion accelerate. And remember, the critical value of matter was 1. This is 0.7, which means that 7/10 of the matter in the universe, of the energy in the universe, is this dark energy, and we do not know what it is. It may be a cosmological constant, or it may be some unknown form of matter. So one of the big things in cosmology, we are pretty convinced there is this dark energy, and we do not know what it is or why it is there. The second great discovery of fairly recent times is that the rotation curves of galaxies, the motion of galaxies, indicate the presence of dark matter. You look at galaxies, how they're moving, and you use Newton's theory of gravity to work out how much matter there should be. You compare it with the motion, and you find the matter you see is not enough to explain what you see. Unseen matter does not radiate, changes the motion. It's felt through its gravitational field, but we can't see it. Now, actually, that's not very surprising if you think about it. If there's a lot of matter out there, there's no particular reason why all of it should be radiating. In other words, there's no particular reason why we should see all of it by the light it emits. And the density of dark matter varies with scale, but cosmologically it's about 0.3. Remember, the critical density is 1, so about 3/10 of the stuff out there is dark matter. But the really amazing thing, the thing we never expected, is that the luminous, the visible matter, is about 0.02 in these terms. It's a very small fraction of the amount which we have determined. And what has been, by comparing what we find from these curves with what we know from nuclear synthesis, which I'll talk shortly, we find that virtually all of the matter, so we've got the energy, the dark energy, we've also got the dark matter. The dark energy pushes things apart, the dark matter pulls things together. This is about 0.3. The amount of ordinary matter, the kind of matter which is in the room, is roughly speaking of this order 0.02, and most of the dark matter is not ordinary matter. It's completely different from the matter in this room. And there's a huge industry out there trying to puzzle out what is the nature of this dark matter, which is most of the matter in the universe. So that's the second great discovery of recent times. Firstly, dark energy. Secondly, dark matter. And the way we work out the dark matter typically is this is a galaxy looking across the galaxy, the distance from the center, and these are the rotation velocities, which you measure by redshift. The measured amount is there, the visible matter accounts for that much, and the difference is dark matter. So this is the typical kind of data you use. Okay. So this is recent times. Now, follow the universe backwards. It was moving apart, so going towards the past, it was coming together. Well, when a gas is compressed, it gets hotter and hotter, so the universe was hotter and hotter in the past. And if you follow it back using standard physics, you can predict it will heat up, and hence there was a hot Big Bang era in the early universe. The thing was like a very, very hot expanding gas. When there's a very hot expanding gas like that, eventually it gets hot enough that the matter and radiation are in equilibrium, and it generates black body radiation. This is a standard form of radiation which is given out by any very, very hot black body, and this was established by Max Planck and other physicists about the turn of the last century, well over 100 years ago. And we've measured this radiation. That was the Nobel Prize for work done in 1965. We find it is there today at a temperature of 2.75 Kelvin. That is minus 270 degrees centigrade. It's just a few degrees above absolute zero. It's very, very cold, which is why it's very difficult to detect. And this radiation has got a characteristic blackbody spectrum, for those of you who know about that. What that means is quite astonishing. It means that quantum physics as we know it today was applicable, exactly the same physics was applicable to the universe 14,000 million years ago. It checks for us that physics hasn't changed in any serious sense over the lifetime of the observable universe. This radiation reaches us from what we call the surface of last scattering at a temperature about 4,000 degrees. I'll give you a picture of that in a minute. But one of the major things which has been done was to look across the sky, and this is a map of the whole sky. Imagine the whole sky around us flattened out onto this two-dimensional screen. These are the hot parts and the cold parts. Now, this is our own galaxy. Do you remember that picture of our galaxy? Well, this is our own galaxy seen in this radiation, so this is near us. But the rest of what you're seeing is the surface of last scattering. It's when this radiation got free from matter about 14,000 million years ago. And at that time, certain spots were hotter and certain spots were cooler. The hotter spots are going to form huge, great big clusters of galaxies in the future. The cooler spots will form great big voids. So these are primeval perturbations which provide the initial data for the structures we see about us today. Now this is the little picture. This is time going from the left to right. It's the size of the universe. So the universe gets very, very large and then it goes rather slow. I'll talk about this in just a minute. So time goes from left to right. Elementary particles combine to give protons at these very early times. So we start here going to the right. Elementary particles give protons and neutrons. Then light elements are formed here 3 minutes after the Big Bang. This happens very, very fast. This is a logarithmic scale with time compressed on the left and expanding on the right. This is the last scattering surface. At earlier times, the universe was opaque. The matter and radiation were interacting with each other so that radiation couldn't move more than a few centimeters before it collided. But then the matter and radiation decoupled, the universe became transparent, and the cosmic background radiation was let free at this time, the surface of last scattering, and that's what we measure today, the graph I just showed you in the last slide. And so this is where atoms were formed. Before that you had a plasma. Atoms were formed. There was a dark era, and then the first stars and galaxies formed, and then later stars and galaxies formed, and we are up here today. So this is a compressed scale, the start of the universe, the formation of the first particles, the formation of the first light elements, decoupling of matter and radiation, the beginnings of stars and galaxies, and then present-day stars and galaxies. Now, One of the things we understand by using nuclear physics is the origin of the elements. Nuclear physics processes, as I mentioned in the last slide, during the hot Big Bang era, started a process of nucleosynthesis when protons and neutrons fused together to form the light elements in the very early universe. This was at about temperature of 10 to the 9th degrees Kelvin, when neutrons and protons combined to form light nuclei. Now, one of the things which was found is the heavy elements cannot be formed in the early universe. Now, that's of considerable importance to us because we are made of heavy elements. So we are made of heavy elements which were not there. If you go back to this last slide, at this time here, all that was there was hydrogen, helium, and tiny bits of lithium and deuterium. There wasn't any carbon, there wasn't any nitrogen, so these first stars could not have planets, they couldn't have people around them because they weren't heavy elements. What happens is the heavy elements formed in the interior of stars. In the inside of stars, elements cooked through nuclear reactions made carbon, hydrogen, nitrogen, oxygen, phosphorus, and so on. And these were then spread through space by the supernova explosions I've already mentioned. Then the remnants of those supernova explosions could then condense again and form second-generation stars, and those stars and the planets around them did have carbon, nitrogen, oxygen, phosphorus, and that's where our elements that we are made from came from. And so that's the basis of the crucial elements of life, and the phrase which you probably have heard, we are all made of stardust. The elements we are made of were cooked up in the interiors of stars. Now, that's the origin of elements. Even earlier than the hot Big Bang era, what happened? Well, in the very early universe, particle physics plays a major role. Quantum field theory, the theory of incredibly small particles and fields, allowed negative gravitational mass. So our expectation that things will slow down wasn't true at that very early time. At that very early time, quantum fields could make things blow apart incredibly fast in a very, very short time. And that's what's called inflation. Inflation took place incredibly early after the hot Big Bang, the start of the universe, with expansion rapidly accelerating through a huge amount of e-foldings. That's a great many multiples before the hot Big Bang era. And this is now the standard model of cosmology. There was this incredibly rapid expansion, followed by the hot Big Bang era, followed by the dark era and the creation of galaxies and stars and structures. And chaotic inflation predicts pockets of inflation surround ordinary expanding universe regions, resulting in an overall fractal-like structure. I'll talk about that in just a minute. At the end of inflation, the field which caused it decays into matter and radiation, as is the start of the matter we see around us. So this is the summary here. You start off on the left, you've seen this already. Something happens there, I'll talk about in a minute. Inflation takes place, and then all of those processes I've talked about take place. This is plotted in a slightly different scale. We are up here with an age of about 14 billion years. So we have a concordance model of cosmology. I've shown you that, the microwave background. What this is, the cosmologist, one of the great triumphs of cosmology was inflationary theory predicted that if we analyze this into the power on different angular scales. Now this is the power on different scales, large scales on the left, small scales on the right, and theorists predicted we should see a series of peaks. And observations then found those peaks. And that's what science loves, prediction, which is then verified. And this happened in cosmology. These peaks in the power spectrum were predicted. And so the standard of model of cosmology has got the dark matter density 0.3, the cosmological constant 0.7, and it agrees with lensing, matter power, spectral velocities. It all fits together in a good standard model. The puzzles, the nature of dark matter, the nature of dark energy. So it's really important to ask, are there alternatives? And I could talk about that, but that's not my subject today. The details of galaxy formation, the details of the matter radiation interaction and structure growth. There's a huge industry looking at all this. Is it fully consistent when we take nonlinear things into account? That's what a lot of people are looking for. And the nature of the inflaton. I talked about this inflationary era, but we don't know what the inflaton was. So we've got three really big puzzles. We don't know dark matter, we don't know dark energy, we don't know what the inflaton was. So it's really important to also look for alternatives to inflation. But many new observations are taking place, deep surveys, cosmic background radiation, polarization observations. There's a vast amount of fantastic work going on with new observations, new surveys for all of these things, trying to sort out the dark matter, the dark energy, the details of structural formation, the nature of inflation, and the big new thing that will happen is gravitational wave observations are hoped to come in and play a role in this in the future. Okay, that's the standard cosmology. Now, where the really controversial starts is, let's start asking what happened even before inflation. What happened before inflation? And this is where we run into quantum cosmology. The question of what did gravity look like at the very, very high energies and very, very small scales when quantum theory has to be taken into account. So quantum effects will dominate, and the problem is we don't have a proper theory of quantum gravity. We've just been talking about that in the meeting that is going on at the moment. And there have been many attempts to describe quantum cosmology, something called the wave function of the universe, something called pre-Big Bang theory, something called brain cosmology, something called the expirotic universe. This is a straightforward attempt to use the Schrödinger equation, more or less. This is based on the idea of string theories. This is the idea that our universe is a four-dimensional space embedded in a higher dimensional space-time, and so on. So there's lots of these theories. The main point I want to say is in all cases, the problem is making a solid link to observational tests, because in every case, the proposed particle interactions and extension of classical gravity is not testable. So all of those theories I've just mentioned are hypothetical. They may or may not be true. The theories are indirectly testable via their effects on inflation and the microwave background spectrum, but there is no fully formulated theory of quantum gravity. So as we follow back, we understand things back very well to nucleosynthesis. We more or less understand inflation. Before that, we are in an area of speculation, okay? And in particular, we actually don't know if there was a start to the universe or not. One of the biggest questions of all, has the universe existed forever or not? And some theories of quantum gravity say there was no start, others say there was. We don't even know yet, at the present time, if the universe had a beginning or not. What we're running into is what I call the physics horizon. The problem is there's a limit to what's testable in the laboratory and in the solar system. We can only test up to certain energies. The LHC you've all heard about, the collider that's making these huge discoveries. It's got a certain energy. It's a very, very high energy, but it isn't as high as is relevant to the very early universe. And we can't build the big enough accelerators because our gross national product isn't big enough, let alone any other problem. So we have to extrapolate known physics to domains when the physics that we're applying to the universe is untested and may be untestable. This is the physics horizon. You can extrapolate in different ways from known physics to what's relevant there, and the outcomes will be different. So uncertainty increases in the very early universe, testability declines, and particularly theories of creation of the universe cannot be tested. I will return to that in a minute. Now, paradoxically, theoretical cosmology is increasingly proposing theories based on ever more hypothetical physics for the reasons I've just said, and even ones that are untestable in principle, and the prime one is the idea of the multiverse, the claim that what we can see, all the stuff I've been showing you, is just one tiny fragment of a very, very much bigger set of multiple universes, each with different physics and different things happening in them. Now, some people claim this is the inevitable outcome of the physical originating processes that generated our universe. This thing called chaotic inflation says there are billions and billions, they even say an infinite number of similar bubbles out there, but with different rates of expansion, different amount of matter, different constants of physics. Some people see this as a result of a philosophical position. The philosophical position says anything that can happen must happen. Anything which is possible is obligatory. And some people believe that's a basic underlying philosophical position. The third reason, and perhaps one of the most common ones nowadays, is it's proposed as an explanation for why our universe appears to be fine-tuned for life and consciousness. This is taken as an explanation for why we, human beings, can exist. So the existence of these multiple universes is because of what's called fine-tuning. Now, the universe is fine-tuned for life, firstly as regards the laws of physics. If you mess around with the laws of physics, if you change the fine structure constant, if you change the strength of a nuclear force too much one way or the other, we won't exist because atoms won't exist. If you change the boundary conditions for the universe, if you make it too lumpy to begin with, everything would have collapsed into black holes. There wouldn't be any galaxies. If you make it too smooth, there wouldn't be any galaxies. You've got to get the amount of inhomogeneity in the early universe right, or we wouldn't be here. The constants of physics must be in the right, and particularly this dark energy. Most people think it's a cosmological constant, this acceleration. If that acceleration was very much bigger, that would have won in the early universe. Gravity would never have won, and galaxies wouldn't have existed. We wouldn't be here. On the other hand, if it was too big and negative, the universe would have done a big whump, a big crash, and there wouldn't have been time for us to come into existence. So you've got to get the laws of physics right, you've got to get the boundary conditions right, and you've got to get the constants of physics right in order that we can exist. So the question is, the philosophical question, why did the laws of physics turn out to be of such a nature that we would come into being as a result of an evolutionary process? If you get the laws of physics wrong or the boundary conditions wrong, no evolution process of any kind will ever start to take place. Now, the physical explanation, which a lot of my colleagues are proposing, is a multiverse. You think of these billions of universes, and each of them, the laws of physics may be different, the boundary conditions may be different, the constants of nature be different. And if you imagine scattering around billions of universes out there, with all of these things varying, then you will be lucky somewhere. Things will work out right somewhere, and life will come to exist somewhere out there just by pure luck. So an infinite set of universe domains allows all possibilities to occur, so somewhere things will work out okay. That's the basic way that the multiverse is used to explain why our universe allows life to exist. Now, I emphasize it must be an actually existing multiverse. This is essential. To think of hypothetical ones doesn't help. For this to work as an explanation, these other multiverses, these other universes must actually be there. And Martin Rees, in his book Our Cosmic Habitat, says, Rees explores the notion that our universe is just part of a vast multiverse or ensemble of universes, in which most of the other universes are lifeless. What we call the laws of nature would then be no more than local bylaws imposed of the aftermath of our own Big Bang. In this scenario, our cosmic habitat would be a special, possibly unique universe where the prevailing laws of physics allowed life to emerge. That's the philosophy of this project. The problem is there's no chance of testing it. The universe domains involved are beyond possible observation, and not only now but for the conceivable future. The furthest we can see is the matter which emitted the microwave background radiation. There's a huge amount of matter beyond that. We can't receive it because there hasn't been time for light to reach us since the beginning of the universe. This is the visual horizon. The supposed physics is also untestable. So some people claim that this must happen because the physics will make it happen. Well, the physics they're talking about is not tested, has not been tested, and is in most cases not ever going to be testable physics. So not only can you not observe it, but the physics isn't testable either. In fact, the main reason it's pursued, in my view, is because it's a good explanation of fine-tuning. That is, it's pursued for philosophical reasons, and many people like Steven Weinberg, Martin Rees are quite explicit in this. They are pursuing it because it provides them with an explanation of fine-tuning, and therefore it is the only scientific explanation they can see of why the universe is friendly for life, allows life to exist. So you see, what has happened here is the requirement that science should be tested has been downgraded relative to the requirement that science should explain. Science you wanted to do be testable and to explain. And so what is happening here is that what these people are saying is don't worry too much that it's not testable. It's a very good explanation, therefore you should believe it. So I ask whether that is science or whether that is philosophy. The big issue is that the very nature of the scientific enterprise is at stake in the multiverse debate. The multiverse proponents are proposing weakening the nature of scientific proof in order to claim that multiverses provide a scientific explanation. They're doing so by saying, don't worry about testability, it's a really good explanation. Well, that's pretty dangerous because that takes us back to before we started the experimental testing. Anybody can have an hypothesis, which is a very good explanatory hypothesis. The whole point, what made science so successful was testing. So they're now proposing untestable theories and say, don't worry about that. Well, I think that's pretty dangerous, and in any case, it doesn't solve the ultimate issues, as I will mention shortly. And again, I emphasize we're concerned with really existing multiverses, not potential or hypothetical. There's no problem with potential or hypothetical ones. The question is, does it really exist out there? I think it's quite ironic when people who, on the one hand, insist that the virtue of science is testability, on the other hand, strongly support a multiverse to explain fine-tuning. I'm thinking particularly of the writing in a recent book by Richard Dawkins, in which he says this provides a scientific explanation of why the universe is fine-tuned for life. Now, Dawkins claims that the virtue of science is testability, but he doesn't think that that is so applicable in the case of cosmology, which is a really interesting thing. I think we must not revert to theory trumping observational tests. I think that takes us back 2,000 years to the pre-Galileo time. I think it's a huge step backwards. I think we must insist that science is about testability. Now, I've had debates with Bill Sturger and others about just how much testability you need, but if you abandon testability, then I think you have left science and you are in the realm of philosophy. Now, let's take this a step further. Many Worlds and One, The Search for Other Universes by Alex Valenkin. He goes on to posit our universe is but one of an infinite series, many of whom are populated by our clones. And he's taking infinity, he means infinity when he says this. Some of these multiverse enthusiasts, they don't just say there's a huge number, they say there's an infinite number. Valenkin is well aware of the implication of this assertion. Countless identical civilizations to ours are scattered in the infinite expanse of the cosmos. With humankind reduced to absolute cosmic insignificance, our descent from the center of the world is now complete. The point is, if you have literally an infinite multiverse out there, the probability of there being a room exactly like this out there is 1. In an exactly identical room out there, I'm saying the same thing to you. In another one, I'm saying a slightly different thing to you. But once you have a probability of 1 of another room like this being out there, there's a probability, there's an infinite number of identical rooms to this, because that's the nature of infinity. The nature of infinity is if the probability of anything is 1, then there's an infinite number of identical rooms out there, exactly the same as this room, and slightly different, and more different. It is a mind-boggling claim that is being made in this book, and I think this is complete nonsense. The often claimed existence of physically existing infinities, of universes, spatial sections, and so on, is dubious. Now, and Bill Sturger's helped me really clarify my mind on this. Firstly, in fact, if you look at their models, this never happens in a finite time. In fact, the universe is always tending towards this number, but it never, ever reaches it in a finite time. And the key point is infinity is not a big number, it's an unattainable state rather than a big number. And David Hilbert said the following: the infinite is never to be found anywhere in reality, no matter what experiences, observations, and knowledge are appealed to. Hilbert, one of the greatest mathematicians ever, knew you needed infinity in mathematics, but he said it could not occur in physical reality, and I think that is correct. But the further point is that claim, that book by Valenkin, he's putting this forward as science. Okay, so is this idea testable? It is not testable. Because the whole point about infinity, supposing there was this infinity out there, you can't see them all, but supposing you could see them, you could still not prove there was an infinite number, because no matter how many you had counted, you wouldn't have proved that it was infinite, because to prove it's infinity, you have to prove there is never, ever an end. And you cannot do that. And so the claim that infinities exist in the multiverse is definitely not a scientific statement, even if the multiverse does exist. Okay, we're also seeing ever more dogmatic claims about how scientific cosmology can solve philosophical problems that have been with us for millennia. And the big philosophical problem is, what does it mean if we discover that our universe must have had a beginning? Supposing we in fact conclude from our theories there must have been a beginning to the universe. How did that happen? What led to it? How do we handle the idea of the creation of the universe? Well, the basic way that you can do that is to assume something in some sense pre-existed, because you have to have something out of which to create something. And in fact, many of my colleagues are producing theories of the creation of the universe in which they're assuming that quantum field theories, Hilbert spaces, group theories, all sorts of things pre-existed the existence of the universe, because they assume that those theories apply to the process that led to the existence of the universe. The only alternative is you give up on causation, or at least in some sense or other. One of the questions is, are there the laws for the universe itself? And the problem is there's only one universe. And the idea of a physical law is it applies to many, many similar objects. If there's only one universe, how can you talk about a law when there's only one thing for it to describe? A law that describes only one thing is a description, it's not a law. And that's one of the problems. But let's go back. As I say, most of these claims are based on the idea the whole structure of quantum field theory is taken for granted and is assumed to lead to the creation of the universe. So where did quantum physics exist before the universe came into existence? Okay, that's the big question which is unanswered in these books. And the recent claim is the universe arose from vacuum fluctuations. Quantum field theory, the theory of the vacuum with no matter there, does not remain a vacuum. Particles bubble in and out of existence. That's one of the great discoveries of the last century. One can extrapolate the theory to the idea that universes might bubble out of the vacuum if the right sort of fields exist, and this kind of tunneling takes place for the vacuum. And this is the idea which Hawking and Mlodinow have put forward in Lawrence Krauss in these books, The Grand Design by Stephen Hawking and Leonard Mlodinow, and The Universe from Nothing by Lawrence Krauss. And the question is, what should we think of this? Now, there's a very, very interesting book review of Krauss's book by David Albert, who's professor of philosophy at Columbia University and an author of Quantum Mechanics and Experience. And he says as follows: Lawrence Krauss, a well-known cosmologist and prolific popular science writer, apparently means to announce to the world in this new book that the laws of quantum mechanics have in them the making of a thoroughly scientific and adamantly secular explanation of why there is something rather than nothing. Period. Case closed. End of story. Look at the subtitle. Look at how Richard Dawkins sums it up. And sorry, can we see the subtitle? No, we can't. Why there is something rather than nothing is a subtitle. So Krauss's book claims to explain why there is something rather than nothing. Look at the subtitle. Look at how Richard Dawkins sums it up in his afterword. Even the last remaining trump card of the theologian, why is there something rather than nothing, shrivels up before your eyes as you read these pages. If on the origin of species were biology's deadliest blow to supernaturalism, where we may come to see a universe from nothing is the equivalent from cosmology. The title means exactly what it says, and what it says is devastating, that the universe could come into being out of nothing. That is the claim. Well, is it in fact well-established physics? Does it solve the philosophical issues that he claims? So first, what is testable and what is not testable in cosmology? Now, this is the picture you've already seen, the time going to the left, and I just want to emphasize what I've already said, but I want to really emphasize it. Now, well-understood physics applies from there through to here. It is speculative physics at that time, and what Krauss and Hawking are presenting to you is speculative physics. It is not tested physics, it's not well-established physics. Okay? A great deal of what Krauss talks about is not tested, well-established physics. The stuff about creation of the universe is not testable even in principle. Equally so, the theory of the string landscape, which they rely on to underlie their claims that this explains fine-tuning, that is not tested. It's not even a very well-defined theory. And the link between chaotic inflation and the string landscape is hypothetical physics. It is not tested. So what they believe is that the constants of physics will vary because of the string theory, which is the fundamental theory of quantum gravity that many people believe in. That's not a well-tested theory. In that theory, there's a theory of the quantum vacuum, which is also not a well-tested theory. And in addition, they're assuming that the inflation is linked to that quantum vacuum. That's also not tested. There are multiple layers of speculation in this. It's a nice picture, but tested physics it is not. David Albert says as follows: where are the laws of quantum mechanics themselves supposed to have come from? Krauss is more or less upfront, as it turns out, about not having a clue about that. He acknowledges, albeit in parentheses and just a few pages before the end of the book, that everything that he's been talking about simply takes the basic principles of quantum mechanics for granted. I have no idea if this notion can be usefully disposed with, he writes, and at least I don't know any productive work in this regard. So the nothing, which he assumes, is in fact the entire apparatus of quantum field theory, which is not nothing by any stretch of imagination. And what if he did know of some productive work in that regard? What if he were in a position to announce, for example, that the truth of the quantum mechanical laws can be traced back to the fact that the world has some other deeper property, X? Wouldn't we still be in a position to ask why X rather than Y? And is there a last such question? Is there some point at which the possibility of asking any further such questions somehow definitively comes to an end? How would that work? What would that be like? What the fundamental laws of nature are about, and all that the fundamental laws of nature are about, and all that there is for the fundamental laws of nature to be about, insofar as physics has ever been able to imagine it, is how the elementary stuff described by physics is arranged. But the laws have no bearings whatsoever on questions of where the elementary stuff came from, or of why the world should have consisted of that particular elementary stuff it does, as opposed to something else or to nothing at all. They have nothing whatsoever to say on the subject of where these fields came from, or of why the world should have consisted of the particular kinds of fields it does, or of why it should have consisted of fields at all, or of why there should have been a world in the first place. Period. Case closed. End of story. Albert is saying that not only is this not well tested, these theories, but these theories can't do what Krauss is claiming. Physics cannot deal with the kind of questions to which Krauss is applying it. So what can we make of recent claims about how scientific cosmology reduces to issues of meaning? Okay? What you've got to get into is the natures of existence. And what I claim is there are both physical realities, but there are also abstract realities out there which are important for the universe. Firstly is the physical laws. The laws of physics control what happens in the universe. And one of the most puzzling questions is, how do the laws of physics control what happens in the universe? Do they exist in some Platonic space and reach down to the material world, or not? In what way do they apply? Because that's incredibly relevant to this idea of coming into being of the universe. Theories like Hawking and Blondel somehow assume that the laws of physics existed before the universe existed. They deny that, but that's actually what they are assuming. So where did the laws exist? In what way did they exist before the universe came into being? That's one of the crucial questions which somehow they don't really tackle. Now, related to this is mathematics, because physics is a mathematical theory, and one of the deep issues is, how does mathematics relate to physics? But one of the things we can say, at least most of us believe, is that mathematics exists out there in a way which doesn't depend on culture, time, space, probably doesn't even depend on the existence of the universe, that mathematics exists in some kind of eternal Platonic space out there. And I want to talk about that in just a minute. There are two big issues: the existence of possibility spaces for physical existence and for mental existence. Now, the laws of physics create the possibility of physical existence. Okay? In the sense that once things have come into being, they describe the possibilities of what can happen, of the kinds of things that can happen. All that comes into existence is foreshadowed and allowed by possibility space for physical existence, the laws of physics. The laws of physics describe what is possible and what isn't. For instance, you can't violate energy conservation. You can't violate momentum conservation. No matter what happens, that's written into the laws of physics, which determines this possibility space of behavior on a football field, in driving a motor car, whatever. You can't violate the laws of conservation of momentum, conservation energy. So there's a possibility space of possible ways you can drive, which is governed by the laws of physics. Now, equally, there's laws of biological existence, the landscape of evolutionary theories. Some animals are possible and some are not. Like, you can't have a pig which is 20 feet long because it will fall flat on its face because of the scaling laws of physics. Animals have to have an energy intake and output. You can't create an animal which doesn't have energy coming, going out. So there's all sorts of constraints on what is possible for animals. That's the possibility space of biological existence. But one of the most interesting ones, there's a possibility space for thoughts. Because, in fact, the brain is a finite system. The brain can only have a finite possible number of thoughts, and the thoughts that you can think are somehow written into a possibility space of possible thoughts. This is the space of possible logic which existed again before the universe came into being. And we discover some of the thoughts that we could have, but we can't think thoughts which aren't possible thoughts. And so there is a space of possible thoughts, somehow in some sense underlying the universe, just as there is a space of possible physics and a space of possible biology. And in fact, there has to be a space of possible emotions, possible meanings, and possible values, which I'll come back to in just a minute. Let me just take mathematics as an example. It's a case of a Platonic world of mathematical abstractions, which we learn about through our human minds. Mathematics is causally effective because it creates patterns on paper. It's used in physics, it's used in engineering, commerce, and planning in general. Mathematics somehow exists, waiting to be discovered. We discover it, we use it, it changes life in the world around us. Major parts of mathematics are discovered, not invented. For instance, the fact that the square root of 2 is irrational was discovered by the Greeks, and it dismayed them to discover it. They didn't want to discover it. It was not a social invention. It was something about the nature of mathematical reality which they discovered. Now, we're convinced all mathematicians throughout the entire universe will discover that the square root of 2 is irrational. It's got nothing to do with culture, time, or place. What that means is, the way I would express it, there's a Platonic world of mathematical realities which we discover, and that is the world of possible logic of mathematical arguments. These spaces have an abstract rather than embodied character. You can't determine mathematics by physical experiments. You determine it by logical experiments, and they are independent of the existence and culture of human beings. In fact, they would have pre-existed the universe. In my view, they must have pre-existed the universe if Hawking and Mlodinow were right, that the laws of physics pre-existed the universe, because the laws of physics assume the laws of mathematics. So these basic geometrical features, the number pi, is somehow written into the fabric of reality in an eternal, unchanging way. Okay? The same result for the number pi will be discovered near Alpha Centauri on the Andromeda Galaxy. Pythagoras' law will be discovered by people out there. And this, the fractal Mandelbrot set, was waiting to be discovered. People didn't invent it. It isn't a social construction. It was sitting waiting to be discovered until we had computers powerful enough to print the set out, and it then surprised everybody. We could understand it after we'd seen it. Nobody predicted that this would exist. It was a discovery in the journey of exploring the mathematical landscape. So the key issue is the coming into existence of things that make these possibilities real, the universe, the laws and powers that underlie it, the existence of life. What makes the specific laws fly? We have the possibility space, and then we have a particular set of the possibilities that's realized, these two things. But the deepest thing, the really deep thing, is why the possibility spaces exist. Where do they come from? What do they express about the nature of the universe? Where does it come from that these kind of entities have any possibility of existence, of matter, of mathematics, of thoughts of a specific kind? What kind of pre-existence allows their actual existence? Because my claim is that, for instance, mathematical theorems can't come into existence unless their possibility was already somehow embedded into the structure of reality, just as the laws of physics are. As I said, there's a finite space of thoughts and possible reasoning. We could talk about this a little bit. The possible length of a meaningful sentence is finite. It is not infinite, despite what some theories of linguistics may say. Why is there any logical basis for things at all? Why are there laws of logic which underlies what happened? The logic is a possibility space for what can happen. And so the claim I'm making is that before the universe came into being, or maybe with it, but I would think before, if there's any sense in which the universe came into being on the basis of something which in some sense pre-existed, the laws of possibilities had to exist, okay? Because that determines the laws of mathematics, that determines what physics is possible, because what physics is possible is determined by what mathematics is possible. But then the really big question then is, I claim that also, as well as these possibilities of physics and mathematics, possibility of ethical behavior must have been there pre-existing the universe also, the possibility of good values and bad values. In fact, so I take the view of an ethical realism, which is basically saying there's also a space of ethical possibilities with a value system there, what is good and what is bad. And the really funny thing about this is that Richard Dawkins and Victor Stenger actually also believe in a moral reality, but they don't realize that they do. And I think that's quite funny. Richard Dawkins and Victor Stenger have written about how Christianity, religion, is evil. Now, one can debate about that. Many evil things have happened for religion, but the point I'm making here is Dawkins and Stenger believe there are absolute values by which you can judge if religion is evil or not. And they haven't thought about where they get their values from, but I claim that what they are assuming is universal, cultural independent, space and time independent values of what is good and what is bad. In other words, I claim that they are thinking there is in fact a moral reality out there by which they can judge the goodness or badness of religion. And of course, I completely agree. I believe in ethical realities, and I wrote about this in my book with Nancy Murphy called On the Moral Nature of the Universe. And so what I think pre-existed the universe is not merely laws of physics and mathematics, but also ethical laws, laws that stated what is good, and, well, I wouldn't call them laws, a space of ethical possibilities, including some sort of value system on that space, judging what is good and what is not. Now let me read this to you. I say to myself as I watch the niece, who is very beautiful, in her this bread is transmuted into melancholy grace, into modesty, into a gentleness without words. Sensing my gaze, she raised her eyes towards mine and seemed to smile, a mere breath on the delicate face of the waters, but an affecting vision. I sense the mysterious presence of the soul that is unique to this place. It fills me with peace, and my mind with the words, this is the peace of silent realms. I have seen the shining light that is born of the wheat. That's from Anton Exupéry, Flight to Eris. I find that an absolutely wonderful feeling, a spirit in that. The question is, where did the possibility of that kind of expression come from? How is it possible that there could be something like that in the universe? The possibility of coming into being of the quality expressed in this text cannot in any plausible way, I suggest, arise out of purely physical interactions alone. There's a higher level of meaning that this kind of interaction by itself than that the physical kind of interactions by themselves can engage with. I think there is a quality of meaning which is quite undeniable, and you see it in art and literature and in interactions which involve ethical things, which in no way can be encompassed in any physical thing as being implied in any sense by physics, chemistry, microbiology. David Albert, I guess, talking again about Christ, it ought to be mentioned, quite apart from the question of whether anything Christ says turns out to be true or false, that the whole business of approaching the struggle with religion as if it were a card game or a horse race or some kind of battle of wits just feels all wrong, or it does at any rate to me. When I was growing up, where I was growing up, there was a critique of religion according to which religion was cruel and a lie and a mechanism of enslavement and something full of loathing and contempt for everything essentially human. Maybe that was true, maybe it wasn't, but it had to do with important things. It had to do that as with history and suffering and with the hope of a better world. And it seems like a pity, and more than a pity, and worse than a pity, with all that lies in the back of one's head, to think that all that gets offered to us now by guys like these and books like these is the pale, small, silly, nerdy accusation that religion is, I don't know, dumb. And he's saying that the kinds of arguments that are being put in these books don't begin to get into the kind of territory from which you can argue about ultimate meaning, but that's what they're claiming to do. So is the ultimate reason for the universe pure chance or probability or necessity or purpose? Those are the four options, and they're all logically possible. It could be chance, pure chance, not probable, just chance. It could be that it's probable, it could be it's necessary, it could be there's some purpose or meaning lying behind it. David Hume emphasized that science cannot prove any of these right and cannot prove any of them wrong. And that is still true. Neither science nor philosophy can give a certain answer. Metaphysical uncertainty remains. And anybody, whether it's Hawking or Mlodinow or anybody else who says science can prove that one of these is right, simply doesn't understand philosophy. If one wants to relate to deeper meaning of personal life, the last option has the most traction. The others, in the end, provide a more tentative relation to morality and meaning, but we do have experience. Morality and meaning do exist in the world. We experience them in our daily lives. And one of the points about all of this is that the multiverse does not solve this problem, because the multiverse simply pushes the problem back. So the multiverse is supposed to explain why this universe is the way it is. Let's suppose the multiverse is a true explanation of this universe. Let's just suppose that. All the same issues arise again. Did that multiverse arise by chance, probability, necessity, or purpose? The multiverse explanation, despite the way it's presented in those books, gives no ultimate answer for anything. It simply shifts it back one step, and the same ultimate issues remain. So the reprise, what kinds of questions do you want to answer? If you want to answer purely physical questions, physical cosmology will tell you all you want to know. And Lawrence's book is good on the physical cosmology. Why does human life exist? That's what I like to talk about, cosmology with a capital C and cosmology with a small c. Cosmology with a small c is just the physical stuff. Cosmology is the capital C, is you're going to talk about meaning. If you want to talk about cosmology with the small c, you can engage with physics and chemistry and so on, that's fine. If you want to talk about cosmology with a capital C, you can't do it on the basis just of physics. You must talk about meaning, morality, beauty, those kinds of things, or you're not even in the right ballpark to talk about those kinds of issues. If you want to talk about how it relates to purpose and meaning, is there just physical causation underlying it? You may claim after you've done it that there is only physical causation, but in order to debate the thing, you must look at the evidence of all of these other things and not just look at the evidence from particle physics and from cosmology, or you're not even taking the relevant data into account. Actually, we do know there is more than physical causation at work in the universe. Purpose does exist and is causally effective. We know that. You must use models and data of adequate scope for the inquiry, which in this case must take into account the genuine existence of purpose and meaning, which we all experience in our daily lives. So don't claim purely physical arguments are necessarily sufficient to investigate issues of meaning. Can there be emergence of a totally new kind of existence ex nihilo? Could the kind of quality that was in that reasoning emerge purely out of physics, purely out of the interactions of particles with each other? I don't believe that for 1 minute. Now, that's a philosophical statement. I can't prove it, but I believe that very, very profoundly. I think that the possibility of these meanings is preordained. There's a possibility space in which the possibility of that kind of expression was written before the universe began. In other words, I believe that there is some possibility of meaning pre-existing the universe, as well as the possibility of physical laws, chemical laws, and biological laws. So can meaning really emerge out of non-meaning? I claim no, it has to be at least foreshadowed in some possibility space, and neither physics nor multiverse solves these issues. That's my claim.